So today we're going to do something, a max flow algorithm that's kind of interesting. It's called push-relabel. Uh, so this is going to be related to amortized analysis, which we did, I guess, before the midterms. It's been a while. Um, and right, so amortized analysis. Here were some kind of examples from class, like we did the binary counter. You know, each the fifth bit only flips once every 2 to the 5th, so it all adds up to a constant number of bits flipped per average when you increment. We also did things like the doubling trick for arrays, lazy rebalancing for trees, how to make a queue out of two immutable stacks. Okay. And all right, so we're going to do these flow algorithms called push-relabel. They'll be the fastest algorithms we see in this class for flow. So that's fun. But the one reason I wanted to present it is not just because it makes for pretty pictures, because it uses amortized analysis and potential functions nicely. And it uses it in a way that's like not just for data structures. Like last time we kind of did data structures, so here's maybe some of the techniques in a different context. Okay, and I also figure kind of getting more practice with flow is good since we've been doing flow. All right, so let me just quickly review what we did once upon a time. We had, for example, the Edmonds-Karp algorithm, which is just a modification on Ford Fulkerson, where each time you find the shortest path, uh, and you route as much flow as possible. And you get a strongly polynomial running time this way. Uh, the analysis put a lot of emphasis on, well, what's implicitly the dual, but was focusing on the distances from the source to each other vertex in the residual graph. And this distance only gets bigger as long as you route along the shortest paths. And that was the key to this analysis. Okay. So, uh, right, right. Okay, so push-relabel is really going to be all about these distances. That's the role that labels are going to play. So let me explain. Okay, so this push-relabel algorithm is going to be maintaining, okay, I'm going to first describe abstractly what's going on. It might be a little bit fuzzy at first, just definition heavy, but then we'll go through an example and hopefully that'll clarify things. So the algorithm is going to be maintaining two things at a time. One is something called a preflow, which is kind of like a flow but more relaxed. It's not as stringent. And the other is a set of labels. Okay, so each vertex is going to have a label between 1 and n or something, or 2n. It's an integer label. And at some level, these are going to play a very similar role to the distances uh, in the Edmonds-Karp algorithm. Okay, so good. All right, so let me explain what a preflow is. Okay, so you're doing flow, you have edges, they have capacities. And the first rule is that you do have to continue to obey the capacities. Okay, so that doesn't change. So you're sending flow on various edges. And the second rule, so before with a normal flow, we had to have what goes in is what goes out, right? Just like it's a path going through a vertex. But in a pre-flow, a vertex is allowed to accumulate some extra flow. So what goes out is at most what goes in. Okay. Now we're eventually going to want to compute a flow where everything goes in and out, but at intermediate stages, vertices may be holding on to extra flow. Okay, so we'll call that a pre-flow. Okay, so that's the idea. I feel like the math notation makes it seem more complicated than it is. Okay. Now, as you have some pre-flow somewhere at some current point in your algorithm, you can still have a residual graph where you decrease the capacity that you used and increase capacity in the opposite direction. Okay, so same notion of residual graph as before. Good. All right, so the more foreign object are these labels. Okay, so the labels are going to be assigning to each vertex some kind of number. Okay, subject to just a couple simple rules. Rule number one is that the sink will have level 0. Is this 0, 1, 2, 3, or am I going backwards? That's right. Okay. level 0, and the source is going to have level n. And some level is going to kind of stretch everything out the whole time. Okay. So those are some kind of like boundary conditions. And then here's the more interesting part. So the source is up here, and you're kind of trying to send flow down to the sink down here. And then vertices are going to be at various points in the middle. And as you do so, the only rule is that and whenever you have an edge in a residual graph, it can only go down by at most one layer. So it's going down by, it can go backwards as many layers as you want, but it can only go down by at most one layer. And those are just these rules that we're going to try to obey. So, right. So the algorithm is maintaining a pre-flow. So some kind of partial flow doesn't quite have a full flow from S to T. And it has some kind of arrangement of vertices, these labels. Um, and to get that set up initially, what you're going to do is you're going to start with your flow problem. And the source has some edges. Okay. And we're just going to push a maximum amount of flow along all those edges and saturate all those edges. So that S doesn't have any outgoing edges anymore. Okay. And now I'll put S at level N, everything else at level 0. And note that since S doesn't have any outgoing edges, because we've saturated all of them, we're not breaking any of the rules. The only rule is that an edge can't go down by more than one layer. S is the only thing that's way up there, but there's no edges leaving S anymore because you've saturated all of them. That means the residual graph will have some edges going all the way back, but that's okay. So edges can only go down by at most one layer. At this level, everything should be kind of confusing and mysterious. Why are we doing this? But that's what we're going to try to do. Okay, good. So we have a pre-flow, and we want it to be a flow. So the basic issue is that there's all these intermediate vertices that have extra flow on them. We want to gradually kind of try to push them down to the sink. So I'll call a vertex active if it has extra flow. Based on your pre-flow, I'm taking in 10 units, I'm sending out 5. I still have 5 left over that I want to somehow get rid of. Okay, so the high level goal is to sort of, try to get that flow, which is sort of sitting at various points in your graph, all the way down to the sink, or possibly back into the source, because you weren't kind of able to get it into the sink. And you're just going to kind of push little units of flow at a time. So we only have 2 operations. We're going to be doing these operations while making sure we follow those rules. Operation number 1, you push along a forward edge. So a forward edge is any edge that goes down a level. So I'm here, and I push it down sort of in the direction towards the sink. Okay. At some level, you can imagine doing an algorithm that's just pushing flow from on any edge, but that gets harder to analyze. So what we're going to find is what these layers are doing, right? The sink is down at layer 0, the source is at layer n. We're kind of trying to push the flow towards the sink. Okay. From a vertex, I find an edge that goes down, I'll push flow. Okay. But you might be holding on to flow, and there are no edges that you can push down. Okay, just based on how things are. In that case, we have our relabel operation. Okay, so I'm a vertex. I have flow. I'm trying to get rid of it, but I can't push down. But that means there's no edges, right? So I can go up a level without creating a violation. And maybe this will free up an edge because there's another vertex I had an edge to in the same layer. So when I go up, now I can push that flow. Good. So some level, it's kind of a simple looking algorithm. It's kind of elementary operations. In fact, this algorithm tends to do very well in practice. Perhaps because it doesn't have to kind of go through the whole graph to make progress. This might be a stupid question. Yeah. High level idea. Oh yeah, yeah. High level, the moral, the the plan, the concept of a plan. Uh, yeah, what is a yeah, the vision. Okay. All right. So let me now kind of get more and more formal. So when you're pushing flow along a forward's edge, what does that mean? So you have some edge in the residual graph that's going from U to V, and U has to have level exactly one more than the level of V. It should be one step up, or the flow should go one step down. And then there should be some residual capacity, and then you're going to push. How much flow should I push? What's an idea? Yeah, just as much as possible. And what are your there's two possible constraints. There's a certain amount of capacity on the edge, or I only carry so much flow. So I should either be able to saturate the edge or kind of discharge myself of all my flow. Okay, so that's I think everything we'll do today, we'll try to push as much flow as possible, which is reasonable. I will mention there's like a scaling version where you do something a little bit different for technical reasons. We're still kind of trying to push a lot of flow in that as well. Okay, so your other operation is your relabeling a vertex to a higher label. Okay, so in that case, you have some vertex U, you have excess flow, but there's just no edge going down. In that case, uh, it's safe to increase the level without risking an edge going down 2 levels. Because it went down 2, then it should have been going down 1 before, and you should have been able to use it. Okay, good. So yeah. Okay, so this is basically the whole algorithm then. So initially, you have the source and you saturate all the edges and you put the source up at level n. So now there's some other vertices, they have extra flow. They originally started from the source and you're gradually trying to move it to the sink. And so each iteration, you're just going to pick some vertex as excess flow. You're either going to be able to push flow down or you're going to level up. Push flow down or level up. Okay. Eventually, it might even show up on the other side of the source and you push back flow into the source. It's not ideal, but it is what it is. Okay, good. Um, well, we have to justify. So it's not at all clear why. So at termination, no intermediate vertices will have flow. Only the sink will have gotten some, and the source will maybe have recovered some. And then we'll need to argue that we have a max flow, which means we'll need some kind of min cut. So maybe keep an eye out for that. So it's not clear at this stage why. Yeah. So the only way for flow to be pushed n+1. Yeah. So this is sort of the algorithm sorting itself out if it finds that it can't. In hindsight, it'll seem like, it just couldn't figure out where to get to T, so now it's kind of putting it back into S. Okay, but yeah, so you guys should be asking lots of questions because this is sort of an absurd algorithm. The pre-configured questions include, do you ever arrive at a flow, let alone a max flow? What's the running time? I claim this is going to be our fastest algorithm we see, but it's not clear why this is going to be any faster than some of the other algorithms we've seen. And does it even terminate? Right? You're just doing these local updates. It's not really clear that you're making progress. Okay, so yeah. Okay, so it's a funny algorithm. So let's simulate it. So what do I have here? I have sort of like capacities on these edges, and I've set up these vertices. And I guess what we'll do is we'll just simulate the algorithm on this relatively simple graph. Okay. Clearly, this you can route 201 units of flow, 100 along the top, 100 along the bottom, and then 1 unit of flow zigzagging. Okay, so let's see if it can do this. All right, so basically, you're going to tell me what the algorithm does, and then I'll update the picture. So what's step 1? Yeah, I guess you actually move S to N, which is it's just like how many are we have? 4, something like this. And we also saturate all the edges leaving S. So you'll have like 100 here, 100 here. And that means in your residual graph, so maybe I should have drawn the residual graph. So you have an edge from X to Y, you have an edge from edge X to T, capacity 100. From Y to T of capacity 200. And then from S to X, you saturated. So this becomes an edge of capacity 100. And from S to Y, you saturated. So this becomes an edge of capacity 100. X has 100 units of flow. Y has 100 units of flow. Yeah, good. That's what I did wrong. Oh, no, I should have sent 200. Yeah, I see. 200. Good. Thank you. Yeah. And this does have an edge of 100. Why did I change the color? Because in the first step we take S and we saturate all its edges. So I just sent 200 units of flow from S to X. So in the residual graph, there's now a backwards edge from X to S. So we're just going to keep updating the residual graphs and lots of erasing and stuff. Okay. All right. So that's step one. So now you have to pick any active vertex and decide what to do with it. Okay. So we'll relabel X. Oh, it should have 200. Sorry. Good. This is a chance to fix it. Like that. Okay. The one should go to where? Oh. All right. Pick one at a time. Which one you want to saturate first? The 100? Okay. So we'll send 100 units of flow to T, and that'll use up this edge. We won't add a residual edge because we'll never push from T. And then this will become, we now have 100 units of flow at X, and then we'll send 1 unit of flow like this. Okay, so this will go, so much to update 1. This is the reason why we run these on computers. This will go backwards as 1 unit of flow. This will become 99 units, and this will become 101. I'm going to omit the residual edges from T because T is a sink, so you won't push flow out of it. Oh, we can't go Y to T yet. We have to relabel Y. Hmm? So we label like this. Something like that, that, and like that. Y still has 101 units of flow. Yeah, something like this. Okay, now what? All right, so we'll send, I guess, 101 units of flow. 101. Good. Oh, I guess this will remain an edge with capacity 99. Something like this. Y will now have 0 units of flow. Okay. And then it should be the residual capacity. Oh, and up there, in the fraction I wrote, you're using up 101 out of 200 units of flow from Y to T. Yeah, because we're currently sending one unit of flow from X to Y. So in the residual graph, I have one that goes from Y to X, capacity of one. So down below, those are capacities of residual edges. Yeah, so the only active vertex left is X. So we relabel once, like this. Uh, that doesn't get us anything, so we relabel again. Uh, I guess I'll redraw it. So like that. You still can't do anything. You relabel again. I'm gonna just relabel it twice and spare you the thing. So you end relabeling to get up here. No, I just skipped. I could have done it slowly. So first you would relabel it. First it would go here, and I would redraw the edges, but we still can't do anything, so I relabeled it twice. There's nothing wrong with being on the same edge. Um, so it looks something like this, and like this. And this will currently have capacity 99, or 99 units of flow, I mean. And now we push that back to S. This becomes 101, okay? And that'll get rid of all the excess flow, okay? And now you've got your max flow. Because there's no active vertices left now. So S and T, so we only look for active vertices that aren't S or T. Well, in the algorithm, huh? Yeah, so I guess what we're going to try to prove is that once you reach this state where there's no other active vertices, you have a max flow, and that would be the official answer to your question. Okay. Now, one thing kind of nice also is when you get to the end of the algorithm, you actually have these empty layers. Yeah. And so like look at one side of the empty layer versus another. So X and S. What's kind of conspicuous about this partition between XS and YT? The S side and the T side. It is, but yeah, I'm looking for something even more specific. Yeah, everything has to go backwards because there's this empty gap. It's also the min cut. So at least in this algorithm, the min cut has magically appeared in one of these empty layers, or separating the two sides. Okay, so that's the idea behind the algorithm. It's sort of a small example, but if it was bigger, it would take like much longer to get through. So hopefully this made sense, what it's doing. Okay, good. All right, so that's the algorithm. Now let's start addressing these questions. All right. So the first question is trying to just help understand what preflows even are. Okay. So preflows, where you're leaving some flow at various vertices. Uh, so here's a claim that I thought would help us understand it. So let F be a preflow. So F is, uh, it kind of looks like a flow, but various vertices have extra flow, which means that these streams are kind of getting thinner and thinner as things get accumulated in between. Okay. Now, normally with an ST flow, if of like 10 units, you guys did on your homework, breaking it down into basically 10 paths, right? Uh, but here we don't even necessarily have, it's not going all to T, okay? But the claim is I can take a preflow and I could break it down into paths so that say a vertex has residual flow 5, I mean extra flow 5. Your path packing will include 5 paths from S to that vertex. If another vertex has 10 extra units of flow, then the path packing will have 10 paths to that vertex. Does the claim make sense? It's a little awkward. Yeah, okay, so that's the trick proof. So we just add some auxiliary edges, okay? And I'll give it just as much capacity as I need to address this excess flow sitting at each vertex. And now I can extend my free-flow into a flow by just routing the excess along this edge, right? So you have obviously a very convenient auxiliary graph, but in this auxiliary graph, you extended your pre-flow into a flow, which you understand well. You apply your homework problem to this flow. And then if you delete the red edges that you added, you'll get back to claim. Okay, so one thing nice is that a pre-flow can always be thought as a bunch of paths that are ending at all these vertices. That also means what happens if there is no excess flow at any non-terminal vertex? I guess it means you have an ST float and all these things. Okay, all right, fine. Okay, so good. All right, so our next question then is going to be about understanding labels. Okay, so these labels, which seem to be sort of be between S and T, and okay. So here is a claim. For any two vertices X and Y, if I look at the difference if they're labels, X and Y. Yeah, I'm at level 5, Y is at level 2 or something. I'm claiming that the distance between them in the residual graph is at least 3, the difference in their labels. No, there's no absolute value, so this is only relevant when X is higher up than Y. Okay. Says that the level of X minus the level of Y is less than or equal to the distance in the residual graph. Question is why? So you can only go down one level with each edge. So if this thing is 3 levels away, downwards, then you need at least 3 edges to get there. Maybe it's inefficient, you actually zigzag, but you definitely need 3 edges just to traverse the 3 levels. See if that's written down. Okay, so but that's it. So each edge goes down 1 level at most. So if some vertex is 10 levels below you, you need at least 10 edges to get there. Good. So what you see with these labels is we're sort of manually managing something that looks like the distances from the Edmonds-Karp algorithm. Good. All right. So what does this say about the distance between S and T in the residual graph? Well, it's at least yeah. So what's the label of S? Always. The label of T is. So their distance is always at least N. And then what does that say? There's no cycle. Well, there could be cycle, but no, it's not saying there's no cycles. There's no path, because any path has at most N minus 1 edges. Okay, so this graph, these rules are actually maintaining that S and T are always disconnected in the residual graph. So one way to interpret this algorithm is actually trying to sort of gradually find a good ST cut. It always maintains an ST cut, but it tries to find a better ST cut. It's sort of a dual algorithm. Okay, still a little harder to interpret. Okay, yeah, good. No, no. So, because an edge is allowed to jump many layers in the opposite direction. You can go up many edges. So if I'm at X and I'm looking at Y, and Y is way above me, I might still have an edge directly to Y. So the rules only limit how far down an edge can go. It can only go down one level, but it can jump up. And I think in our final configuration, for example, that came up. Yeah, so by the end, like we have this huge edge from Y to X because we had some flow from X to Y. So that's jumping back an arbitrary number of layers, and that's okay. Okay, good. Okay, good. All right, here's another lemma. We're gradually piecing this together. The next claim. If a vertex is active, then its level is at most 2n. Why? You guys actually have all the information you need from the previous two lemmas. If a vertex has extra flow, then its level is at most 2n. This would be very useful because one degenerate condition is you have some active vertex and just keeps relabeling, and never ends, right? This says that there's some limit. Yeah. If the level is greater than 2n, it's disconnected. Okay, but why is that an issue? You can't disconnect. Why can't you disconnect it? There's a precise reason why. So if I'm carrying 2 extra units of flow, then I can think of the preflow as some kind of path packing that includes 2 paths to me from S. If there's 2 paths from S to me, then the residual graph there must be 2 paths back to S. But if there's a path back to S, then the distance can be at most n minus 1. So it can't be 2n. Okay, so that's why we need this observation about preflows. Okay, so the suggestion was kind of right. So as long as V is taking in flow, you should somehow be able to get that flow back to S along the path. Okay, and that limits how far up you are. Okay, gradually making progress. Now we're going to put everything together. Okay. Good. Sorry? S is always fixed at n and t is always fixed at 0. We never actually touch those vertices during the algorithm. We just push and relabel everything else. Okay, so here's maybe the bigger claim now. All right, so you run the algorithm, and at the end, you've pushed all the flow back into S and T. No one else has flow. That means you're conserving flow at all your vertices. What goes in is what goes out because there's no excess. So now you have a flow. Okay, so at the end of the algorithm, you have a flow. And the question is, or the claim is, F is a max flow, and 2, there's at least one empty layer in between, just because S and T are at 0 and n, and there's only n minus 2 other vertices. There's some empty layer. And if you took the S side to be the S side of the cut, and then, in other words, the empty layer should separate a minimum ST cut. All right, so the question is why? Yeah, so let me draw, let me maybe draw a picture. For context, you have S, you have T, and at this point you have some kind of flow. So this is not the residual graph, this is the flow. And not only that, and you have various vertices all over the place at various levels. Um, yeah. Yeah. So these are like your layers. Maybe I should have drawn the vertices better. Oh, that's true. I could have done a doubling trick. All right. So Most of these layers have vertices on it, but there's one empty layer. Okay? And the claim is that if I separate it at this empty layer, that'll give it ST cut, certifying the max flow. Right? All the vertices one side versus the other. So it is an ST cut because S is on one side, T is on the other. But why do I know the size of the cut matches the flow? Sorry? Uh, okay, so I've drawn in blue the flow that you arrived at. If you just kind of keep track of all the edges with water going along it. So basically we're claiming that if you had sort of drawn all these edges going this way, they should equal the size of the flow, right? Somewhere this empty layer needs to play a role. So what does the empty layer imply? So are there any edges in a residual graph going from S to T? Why? No, there could be excess flow, but there's no edges left. It's not because there's no excess flow. How do I know there's no edges left in a residual graph from the S side to the T side of this cut? You can only go down one. I think this came up earlier. We have this empty layer. An edge can only go down one. It can't hop over two. And because you're able to separate everything with empty layer, you know there's no residual graph that's crossing over. Okay? So that means if there were edges in the original graph going from the S side to the T side, you must have saturated all of them with the flow. So the size of the flow is going to equal to the number of edges going across because you know you've saturated that cut. Okay? You know you're not sending flow backwards because that would give you an edge going forwards as well. Okay, so you have a flow and you have an ST cut that's completely saturated by the flow. And then they certify each other to be max and min. Yeah. So the only rule is you have to make sure there's no edge that goes down by more than one, right? So what was the first steps of the algorithm? Do you remember? Yeah, so I saturate all the edges out of S, and then I set S to level N. But since I've saturated all the edges, there's no edges in the residual graph leaving S. So I'm not breaking any rules. There's some backwards edges that are jumping up N levels probably, but that's okay. That's allowed. Yeah. The whole algorithm is like a little magical. Okay, but at the end, you arrive at a flow because you've gotten rid of all your excess flow, and that empty layer is going to, you're guaranteed an empty layer because there's like N plus one layer, it's a pigeonhole thing, or the opposite of pigeonhole or whatever. Uh, and into the flow, saturating ST cut, you're done. Good. We haven't even done the amortized analysis part. Okay, so that means you just run this algorithm, and as soon as there's no active vertices, you have a max flow and you're happy. Okay, if you want the cut, you just find the empty layer. Okay, so good. So now we know why the algorithm is correct. Now it's a running time, which was the declared purpose of the algorithm, of the lecture. Okay, so basically we want to bound the number of relabels I do and the number of pushes I do, because that's basically all the algorithm does. Okay. Within pushes, there's two kinds of pushes. You guys already kind of enumerated them. So we're going to push as much flow as possible, which was limited by what two things? Yeah, so if I use up an entire edge, I'll call that a saturating push. And it's a little confusing. If I don't, and I instead use all the flow coming out of a vertex, I'll call that a non-saturating push, even though you might argue you're saturating the vertex, but that's the point. Okay, so saturating is for saturating an edge, non-saturating is for everything else, which means you kind of discharged and deactivated the vertex. Okay. That's standard term. Yes. Depleting push? Oh, we can do depleting push. Okay. Good. So we're going to try to relabel, bound the number of relabelings, saturating pushes, non-saturating pushes. We need to kind of deal with saturating and non-saturating differently. Okay. All right. First claim, the number of relabels you do is at most n squared. Why? Yeah, 2n. So the max label is 2n. You're always going up. So 2n squared, n for each. Okay, no big deal. Okay, here's the next one. Number of saturating pushes. That means I use up the entire edge. Is at most mn, which is really n per edge. Why? So how come I can saturate an edge at most n or so times? Yeah. Like saturated once for like. Okay, so if I saturate this edge, the edge disappears from a residual graph because I've used it up. And what would it take for it to come back? Push in the opposite direction. But then what has to happen? This needs to be on the other side of me because it needs to go down, right? So like so this, removes an edge, uh, and in a reverse push requires the endpoints to go up. Nobody wants to watch me write this. Okay, good. Okay, now reverse pushing like a okay. All right, here's the last claim. The number of non-saturating pushes is at most mn squared. The number of non-saturating pushes is at most mn squared. Because? Okay, so if I discharge all my flow, the argument is some other vertex has to leapfrog me before I get flow again. But there may be, at any point in time, several vertices with extra flow. In particular, I discharge my flow, there may already be someone there ready to give me flow. Same as before, but it's still active. But it's like still inactive. Sure. Why does that help us limit the number of these non-saturating or depleting pushes? Yeah. For each given edge. So, okay. So my concern is that, okay, I set my flow and there's someone there who already had flow. He just sends me more flow. Why is that limited? There's lots of vertices with extra flow at any given point in time. Well, maybe when I get flow from the next guy, it doesn't saturate the edge, it just saturates the vertex or something. But then the next guy just gets vertex from someone else or something. You can kind of imagine pulling flow down a path or something. So I don't actually know a direct argument. I only have in mind a potential function. Maybe something direct is possible, but anyone think of a potential function? Okay, sum of all. So, okay, I could sum over all vertices the label of V or something, right? Uh, but why? Uh, so why would that go down? Or what does that have to do with saturating pushes? If I do a saturating push, the potential doesn't change. Well, we can modify this a little bit. Minus the number of active plus the number of active. You do want to integrate active into this somehow. Ah, okay. Suppose I sum up over all active vertices the label of V. So I'm a vertex, I'm active. I'm going to push down flow. Okay. But I'm going to deactivate myself. So you'll at least go down by whatever my level is. But it might go up too. Why might it go up? Yeah, the next vertex might get activated. But what's their level? One less. So the net decrease will always be one. Okay. So with this potential, I can pay off all the non-saturating pushes. Okay. The only catch though is now we have an amortized time for the other operations because they increase the potential, right? So a non-saturating push potential will go down by one, right? But we have to pay for things going up from the other operations. Okay, so if I relabel, will the potential go up or down, and by how much? Up by at most one, and you're going to relabel like at most n squared time or something, right? So this will go up by at most n squared over your algorithm. And then what about a saturating push? Saturating push, I have some flow. I don't send all of my flow, but I send enough flow to get rid of an edge. But I might still be active. Oh, but the person I send flow to might not have been active. So it might go up, right? What's the most it can go up by? Yeah, what's the max level? Yeah, so maybe it goes up by 2n. Okay. And how many saturating pushes are there in the whole algorithm? We just did this. Mn. So saturating pushes may increase your potential by at most mn squared. N for each one. Labels will increase by a total of n squared. And then meanwhile, each of my saturating pushes will make it go down by one. So the total increase is mn squared, so I can only go down mn squared times. Okay, so that bounds the number of saturating pushes at mn squared. Yeah. It might decrease by even more than one then. So I will at least deactivate me. So if I'm at level 10, it goes down by 10 right away. And if the person I push to, was not active, then it goes back up by 9. So in net, it goes down by 1. If this was already active, it'll go down by 10, but that's even better. So we have this potential function, and every time I push, I get to decrease the potential function by 1. And it's always non-negative, right? And so then to limit to figure out how many times I push down the potential, it's sufficient to figure out how much the potential goes up over the course of the entire algorithm. It only goes up when you relabel or do a saturating push. Each relabel increases it by 1, there's n squared relabels. Each saturating push increases by n, there's mn saturating pushes. So the total increase to phi is mn squared. So that means the total number of times I can decrease phi by at least 1 is mn squared. Okay, make sense? Uh, I can't think of one, but I'm under the impression it is tight. However, we're going to, well, let's see. Um, okay, any other questions? Yeah, so now we have something like this. Yeah, so each non-saturating pushes will decrease that potential by 1. Relay will always go up by 1. Uh, yeah, yeah. No inequality. We're just friends here. Yeah. Okay, good. So, there's n squared relabels. So what's the total running time? We add all this up. Okay, so you get mn squared, which I guess is the same we had for Edmonds Carp, so we haven't improved anything yet. Okay. But it's still kind of funny that you recover Edmonds Carp doing this silly algorithm. Okay, so can we do faster? Any ideas? Actually, yeah, that's what we're going to do. Okay, so we're going to do just a more specific version of the algorithm. Of all the active vertices, I'm going to pick the one with the highest label and try to push down. Okay, we're going to try to get better bounds this way. All right, good. So since this is a special case, all our previous analysis still applies. The only question is, can we do better than mn squared? That was our bottleneck. Okay, so the claim is that we can do n cubed and claim it only takes n cubed this way. If you do top down, there'll only be n cubed non-saturating pushes. Believe it or not, you guys got pretty close to this earlier. So how can we try to get a different argument? So I'm the highest label vertex, and I've discharged all of my flow. How can I account for that? Since now I'm actually the highest. This didn't apply before because I wasn't the highest. Now that I am the highest, I can only get flow if someone else with flow somehow gets lifted above me. Okay. So each of my discharging flows, I can charge to the next person that got relabeled enough for me to get flow. Okay. Now there's n other vertices, each of which get relabeled n times. So that means I can only have n squared of these discharging things. And there's n of me, so we get n cubed. Okay. So that one's actually almost easier because you don't need a potential function. Okay. Good. Great. Now I have an n cubed time algorithm. That's better than we had before. Okay. We're going to try to do a little bit better. We're going to try to get n squared square root m. So if it's a sparse graph, you're going to get n to the 2.5. This is quite tricky. You're going to need a potential function. Any ideas? This is really hard to guess, but still want to give you guys a chance. Yeah, it's going to kind of come from like balancing terms at the end. Yeah, this is probably also the most bizarre running time we've seen so far, right? Silly's okay. It's the end of the year. We're all a little tired. Silly's okay. What? Yeah. So always try to find an active vertex very close to the cut. Is there always one? I've never heard that suggestion before. Well, first of all, that's an interesting idea. So I guess there maybe the intuition is like, let's just try to focus on the cut. That seems like the critical thing. Um, sure. Okay. Uh, we'll just leave that out there floating. We're actually going to try to show that the existing algorithm, the top pushing from the top, will get you n squared squared m. So we're not necessarily modifying the algorithm. Right? Maybe I can. I don't know if the potential function will even give away much. Okay. So here's what the potential function we're going to use. I'm going to sum up over every active vertex v. How many vertices have label less than equal to mine? Okay, so if I'm active, then I just count how many vertices, including myself, are here on down. Okay, this seems like it can be a very big potential function since, yeah. No, I think it's all W. If that's a mistake, we'll figure it out, but I think it's all W. Okay, so that's sort of a more exotic and less obvious potential function. Okay, I should have blanked that out. Is it too late? It's too late. Okay. Okay, so I'll just go through it slowly. If I relabel a vertex, right, I'm at this label, I might kind of leap onto a level with at most n other vertices and increase everything by n. Okay, and a saturating push, what could a saturating push even do? Would a saturating push ever increase? So why would the potential go up if I did a saturating push? You activate a new vertex and there could be up to n vertices kind of beneath it. Okay, good. So that means the total potential can go up by how much? There's n relabels, mn saturating pushes. Uh, uh, but it's on a per push basis, per bush. Push. Yeah. One push is just an active one vertex. Okay, so the total increase is going to be at most mn squared because in particular is mn saturating pushes. The n squared relabels get dominated by the pushes. Okay. Huh? Yeah, I think that's supposed to be like the number of. So I think I should have wrote more formally absolute value of the set of. Just the number of vertices beneath me. Okay, so from here, okay, so now what happens when I do a non-saturating push? Well, I was active and I deactivate myself. So I get back as many points as there were elements less than equal to me. So it will go down by how much? Well, however many elements are less than equal to me. Okay. All right. So somehow I want to argue that like, oh, okay, one sec. So this should be less than equal to? Yeah, yeah. It should be less than equal to. Okay. So here's what happens, right? So I'm at this level. Let's say there's 100 vertices at this level, and then there's 900 vertices underneath me. So I'm currently adding 1,000 to the potential. I do a non-saturating push. I get rid of myself. That's minus 1,000. But I might activate someone else who puts 900 back into the tally. So the net decrease is just 100 because that's how many vertices were exactly at my level, right? Because when you do a saturating push, you might reactivate a new vertex. So if you subtract that out, all that's left is you're decreasing by the amount in your own level. All right. So then ideally, what would you want? If you can argue that the potential goes down by a lot, that would be really good, right? Because then you're decreasing the potential by so much. Now you can only decrease the potential by a ton, a limited number of times. So what would that look like if the potential goes down by a lot? You have a lot of vertices on your own level, right? Okay, but on the other hand, then what's the bad case? There's only a small number of vertices on my own level, right? The potential doesn't go down much. But that could also be kind of good. Because if I'm like focused on level 100 and I'm just trying to get rid of all the active vertices at level 100, and my issue is that there's not that many vertices at level 100, but the good news is there's not that many vertices at level 100, right? So there's kind of two good things going on. Either there's a lot of vertices, I make a ton of progress on my potential, or a small number of vertices, which means it won't take me long to finish kind of dealing with this level and going down. The algorithm will. Okay. So good, we're almost done. Uh, okay, so I'm going to pick some parameter k. It's going to be chosen to balance things, and say that one of these pushes are going to be big if you have more than k vertices at this level, and small if there's at most k. Okay, and the claim is that there's at most mn squared over k big pushes, and at most n squared k small pushes. Okay, then you would just choose k to balance these terms, and that's where the squared m appears. Okay, good. See if I can remember this. All right, so I first want to claim that there's at most mn squared over k big pushes. Why? Yeah, so each push, big push decreases the potential by k, and the potential is bounded above, I mean, the total increased potential is mn squared. Yeah, nothing written there. All right, next one. Uh, there's at most n squared k small pushes. Why? This is basically the only claim we need, and we're done. There's at most n squared k small pushes. So let's divide the algorithm into what we'll call phases. Each phase is where you're focusing on whatever the current top level was an active vertex is. So I focus on this level for this phase until there's nothing left at this level. I move down a level or something, and maybe I focus on this for a while. Maybe I relabel and then start a new phase again. Okay, so a phase is some stretch of the algorithm that's treating vertices at the same level. Okay, so first, how many small pushes can I have in one phase? So I'm just focused on level 100. I pick an active vertex. I do a non-saturating push, a small non-saturating push, small non-saturating push. How many small non-saturating pushes can I do? K. There's only K vertices on my level, so there's only K active vertices on my level, and that's it. Okay. And then I go down. Okay. So each phase has K small pushes. There's only K vertices. Why is there almost n squared phases? Okay, so certainly I can only have n squared phases where I relabeled something first, but does that really account for all the times I go down? Does the question make sense? So certainly the relabels will account for the phases where you go up. What about the phases you go down? I want to argue that you can only go down as much as you went up, but why? Well, if you track that top level throughout the algorithm, it's like an elevator. It goes up, it goes down, it goes up, it goes down. And you say, oh, well, I had some measurement and the total amount it went up was 1,000,000. Then of course the total amount you went down can be at most 1,000,000. You can only go down by as much as you've gone up. Even if you go up 5 and down 2 and up 4 and down 3 and it's zigzagging, still the total amount you went down can be no more than the total amount you went up. So just by your intuition was right, just by accounting for how much it went up, you also get for free how much it went down. But you need to at least articulate this elevator logic. Does that make sense? Uh, no, the reason why there's only so many big pushes is because the potential can't be negative. So the potential is the total increase is mn squared, and each big push will decrease your potential by k. There's lots of vertices, so there's mn squared over k. The reason why there's only n squared k small pushes is because within a phase, you're focused on one level, and because it's a small push, there's only k vertices at that level. And each small push addresses one of those vertices, so you can only do k before you've addressed all of them. And you go down a level because you've treated all k. And then after that, how many phases there are? Well, there's only n squared phases where you go up because those require relabelings. And then that means there's only n squared that goes down because it's like an elevator. I mean, you can kind of write out elevator in a bunch of equations, but it's not that interesting. And so that's it. All right. So that would be a much more subtle kind of potential based argument that never changed the algorithm, right? It was a natural algorithm. It's an intuitive algorithm. You guys suggested it yourself, but a much more subtle analysis got you to n squared squared m. Okay. That's all I had today. Yeah.